Welcome to FORSEdu.
In continuation of our series of Total Quality Management, we present to you the 5th episode of the series. Our topic for today's video is Failure Mode and Effect Analysis, that is FMEA. To help understand FMEA, let us consider an example of a pharmaceutical manufacturing setup. This is a pharmaceutical factory where 100 bottles of cough syrup are made of glass bottles every day. Out of every 100 bottles, 10 bottles are spilled due to breakage in the bottle while transferring it to filling lines. The pharma company complains to the bottle manufacturer about the breakage of the bottles and warns to end the contract if this happens again. The bottle manufacturer is confused about what to do next. He seeks the help of the operations head, and here is what he says.
Sir, do not worry. We will identify the reasons causing breakage and failures. Have you heard of the concept called FMEA? If not, let's first understand it.
FMEA stands for Failure Mode Effect Analysis, which is a systematic method of total quality management to identify risks and anticipate causes of failure of process and products so that it can be prevented. The goal is to provide an analytical technique giving ratings to assess how significant is the impact of failure on the product or process or customer. This forms the severity rating. How likely is the cause of failure mode to occur? This forms the occurrence rating. How likely is the current system to detect a cause of failure? This forms the detectability rating. Let's understand each of these ratings in detail. Severity rating gives the extent to which the damage is likely to occur. Lesser the damage and inconvenience, the lower the rating would be. This table gives an understanding of how the severity rating is calculated. For example, if the breakage is affecting or injuring the employees or customer, it will be rated 10. If the breakage of the bottle results in failure of the subsystem, then it will be rated as very high. Failure of operation causes the entire operation to halt since it affects the entire production, and hence it is rated at 8, which is very high. If the failure is not noticeable to the customer and doesn't have any effects, then it is rated 1, which is the minimum value, which indicates no severity. Occurrence rating is determined based on the frequency with which failure is likely to occur. Higher the occurrence, higher the rating. For example, if the occurrence of failure is taking place each day, then it is a very high rate. Suppose if the breakage of the bottle is happening each day, then it can be rated as a very high occurrence. Then it might be rated 10. If the breakage is occurring once every 3 months duration, then we can rate it at 6, which indicates that failures are not very high but they are frequent. If the failure occurs once in 5 years or less than 2 occurrences in 1 billion events, we say it has remote occurrence and failure is unlikely and rate it as 1. Detectability rating estimates how well the controls can detect either the cause or its failure mode after they have happened but before the customer is affected. Longer, difficult or uncertain inspection or detection systems will have higher ratings. For example, in this case, the more unfavorable situation will yield a higher rating. Rating of 10 will be given if the cause of failure is undetectable. Rating of 1 is given if 100% automatic inspection is done along with proper inspection equipment. It is then regarded as almost certain it is to find the defect. For the manual inspection process, chances of error are high as compared to an automatic process, so higher will be the rating. Risk priority number or RPN is the mathematical product of numerical severity, occurrence and detectability ratings. RPN is used to prioritize failure modes that need attention first. Higher the RPN number, more is the priority. Let's now solve the supplier's problem using the FMEA approach, listing key details on the FMEA sheet.
Oh yes. Now we can apply FMEA concept in bottle making process and identify the issues and solve the leakage problem. Let us look at the steps involved to solve our problem. First, is the identification of the problem. That is breakage of the glass bottles in the downstream processes. Second, is to determine each process steps and failure modes and anticipate effects and then allot severity rating. Third, is to indicate what is the cause of the problem and determine its occurrence. Mention the occurrence rating in this step. Fourth, based on the controllability and the inspection of the process, determine its detectability rating. Fifth, and one of the most important steps, calculate the RPN using the severity, occurrence and detectability ratings. Sixth, determine corrective actions to improve the system and assign responsibilities to the people. Lastly, implement the actions and then calculate the new RPN.
The problem can be identified as breakage of glass bottles in downstream processes.
Potential failure mode will be uneven distribution of glass while manufacturing. The uneven distribution of glass will result in the formation of the non-uniform cross-section of the bottle. Effects of failure will be 1. Formation of thin at shoulders, body or bottom area. 2. Breaking of the bottle during handling. Breakage of glass bottle may cause spillage of liquid inside it and makes bottle unfit for further use. Referring to the severity table, we can see the ratings. It is important to maintain a uniform temperature throughout the cross-section of the bottle to ensure uniform distribution of glass. So the cause for the formation of thin at the shoulder is uneven glass temperature. Batch production of glass normally occurs in uniformly controlled temperature by temperature sensors. So the occurrence of failure due to uneven glass temperature is infrequent and low and hence given occurrence rating of 4.
The improper holding of molten glass or gob in blank while manufacturing results in non-uniform pressure on the surface of molten glass, resulting in a thinner cross-section. This will lead to a breakage of glass while manufacturing. The occurrence of this is moderately high and hence we give it an occurrence rating of 6. Electronically controlled temperature sensors monitor glass temperature and hence given a lower detection rating of 2. Proper holding of gob in the blank can be ensured by manual checking of deflector alignment with blank. Since this is a 100% manual process, its detection is low and its detection rating is high as 6. In this step, we will do a product of severity, occurrence, and detection rating to get an RPN number. Priority is given to eliminate the causes of failure with a high RPN number. The improper holding of molten glass in blank while manufacturing has an RPN number of 288, which is the highest. Corrective actions are to be taken to reduce risks. An automated system for checking deflector alignment can replace the manual system to improve the detection system. This will help to reduce the risk priority number. Proper maintenance and timely calibration of sensors can help to reduce the risk of the non-uniform temperature of the glass. Results are monitored post-implementation of action and new RPN number is calculated for improved system. Thus we conclude by saying that FMEA is a continuous document maintained by the Quality Control Department to continuously monitor the quality of products and improve upon processes.
That's it for today's video. Hope you liked this video. In the next video, we will be discussing House of Quality, also known as Quality Function Deployment. So stay tuned. Please like, share, and subscribe to our YouTube channel. And press the bell icon to get notifications of our videos.